It is 10:39 at night. On October 9, 1963. The valley of Longarone, in northern Italy, is winding down. Men are finishing their glasses of wine, in the cafes. And children are already asleep in their beds. The air is cool and crisp, typical for an alpine autumn. But then, the atmospheric pressure drops violently. It does not drop, because of a storm front moving in from the Adriatic. It drops because the air is being pushed out of the valley by something colossal. Imagine standing on the balcony of a house in Longarone. You look up toward the narrow gorge of the Vajont River. You cannot see the dam from here, but you know it is there. It is the pride of Italy, the tallest double curvature arch dam in the world. A marvel of concrete engineering, rising 262 meters into the sky. It is a masterpiece. But tonight, the masterpiece is about to become a tombstone. At this precise second, 3 kilometers away, the side of a mountain called Monte Toc is detaching itself from the earth. This is not a rockfall. This is not a landslide, in the way you understand the word. This is a collapse of geological anatomy. 260 million cubic meters of rock, forest, and earth are sliding simultaneously. To visualize that volume, imagine a block of solid rock, the size of Manhattan, digging its heels in, and failing to hold on. The friction that has held this mountain together, for millions of years, has been defeated by water pressure and human arrogance. The mass begins to move. Usually, landslides start slow, and accelerate. This one does not. It accelerates almost instantly, to 110 kilometers per hour. The sound is not a rumble. It is a scream. The frequency of millions of tons of limestone grinding against a layer of wet clay. The mountain is falling into the reservoir behind the dam. This is where the physics of fluids becomes the physics of a bomb. The reservoir is filled with 115 million cubic meters of water. When the mountain hits the lake, it does not just splash. It displaces the water with such violence that the liquid loses its ability to flow and behaves like a solid projectile. The mountain fills the basin. In less than 45 seconds, the water has nowhere to go but up. A wave rises. It is not an ocean wave. It is a wall of water, rising 250 meters above the crest of the dam. That is taller than the Golden Gate Bridge. It scrapes the vegetation off the opposing mountain slopes, scouring the bedrock clean. But the dam holds. The concrete wall, designed by the greatest engineers of the 20th century, withstands a force 10 times greater than what it was built for. The dam survives. But the valley below does not. 50 million cubic meters of water crest over the top of the dam. It is a vertical waterfall, 250 meters high, crashing down into the narrow gorge below. As this water falls, it compresses the air beneath it. This is the detail that most history books leave out. Before the water even touches the town of Longarone, the shock wave of compressed air hits it. The air blast is stronger than the shock wave from the atomic bomb dropped on Hiroshima. It travels at supersonic speeds. It levels buildings instantly. It strips the clothes off victims. It turns windows into shrapnel. The town is dead before it even gets wet. Then, the water arrives. It is moving at 80 kilometers per hour. A slurry of mud, rock, and debris. It does not flood the town. It erases it. It scours the valley floor, down to the bare rock. In less than 5 minutes, 2,000 lives are extinguished. The topography of the region is permanently altered. How did this happen? How did the brightest minds in civil engineering miss the fact that they were building a reservoir on the side of a mountain that was biologically destined to fall? To understand this, we have to look at the geology of the Piave Valley. The mountain is named Monte Toc. In the local dialect, Toc means walking, or crumbling. The locals knew the mountain was unstable. They called it the Walking Mountain. But the engineers saw only the potential for hydroelectric power. They saw a narrow gorge, perfect for a high-arch dam. They drilled boreholes, but they drilled them in the wrong places. They missed a crucial layer of clay, millimeters thick, buried deep within the rock. This clay is special. It acts as a lubricant. When it is dry, it is stable. But when you fill a reservoir, you saturate the rock walls. The water seeps into the microscopic fissures of the limestone. It reaches that layer of clay. The water pressure reduces the effective friction, holding the mountain layers together. It is exactly like hydroplaning in a car, but on a geological scale. The mountain was floating on a thin film of pressurized water. As they filled the dam for the first time, the mountain began to creep. It moved millimeters a day. Sensors detected it. The engineers were worried, but they thought they could control it. They believed they could slowly raise and lower the water level to gently settle the landslide. Like easing a car down a steep hill, they treated a 260 million ton geological fault like a mechanical system they could calibrate. This is the fatal flaw of engineering without respect for nature. They assumed the slide would be slow. They assumed the mountain would slump, not collapse. They did not calculate the velocity. They did not understand that once the friction coefficient dropped below a certain threshold, the potential energy of the mountain would convert to kinetic energy in a heartbeat. Understanding this force is the only way to survive it. If you are ready to decode the universe with us, make sure you are subscribed. Let us return to the moment of impact. The energy release of the mountain hitting the water was calculated to be nearly double the energy of the Hiroshima bomb. The water that went over the dam picked up boulders the size of houses. Survivors described a wind that felt like it was tearing their skin off. This was the displacement air. When 50 million tons of water occupy a space previously occupied by air, that air has to move. It was compressed into a jet stream, channeled by the valley walls. The pressure wave shattered the internal organs of people who were not even touched by the water. In the aftermath, the silence was heavier than the roar. The sun rose on October 10th, over a valley that looked like the surface of the moon. A vast plain of gray mud. The dam still stood, intact. A mocking monument to technical perfection and strategic failure. Behind it, the reservoir was gone, replaced by a mountain of rock. The water had been ejected entirely. The tragedy of Vajont is not just about water and rock. It is about the specific density of arrogance. The engineers and geologists had seen the warning signs. They had seen the cracks opening in the ground on the side of Monte Toc. They had heard the deep subterranean thumping sounds as the rock layers began to shear. But the economic pressure to complete the project, to generate electricity for a booming post-war Italy, drowned out the geological reality. They tried to lower the water level. In the days before the disaster, they were frantically draining the reservoir, hoping to reduce the pressure on the slip surface. But by lowering the water, they may have actually triggered the collapse. By removing the buoyancy that was supporting the toe of the mountain, they left the massive weight of the rock unsupported, slick with the water that was still trapped inside the fissures. It was a no-win scenario, created by the very first decision to pour concrete in that gorge. Today, the Vajont Dam is a ghost. It is disused, holding back a mountain of earth, instead of a lake of water. You can visit it. You can walk across the top of the curve. It is a chilling experience. You look down one side, into the abyss of the gorge. And you look down the other side, onto a grassy slope of debris that used to be a mountain. It is one of the few places on Earth where you can see the direct aftermath of potential energy winning the war against civil engineering. The physics of the event serve as a dark masterclass in fluid dynamics. When the landslide entered the water, it created a tsunami generated by a solid object interaction. The mathematics of this are complex, because the water is not just a wave. It becomes a multi-phase flow. It mixes with the soil and rock, increasing its density. A wave of pure water hits with a certain force. A wave of mud and rock hits with a force that is exponentially higher, because of the increased mass. When this slurry hit the canyon floor, it did not flow around obstacles. It smashed through them. The kinetic energy was so high that the water climbed the opposite side of the valley, wiping out villages that were hundreds of meters above the river level. This is something most people do not intuitively grasp about high-velocity fluids. They do not seek the lowest point immediately. Their momentum carries them uphill. Gravity takes seconds to overcome the initial velocity. In those seconds, entire communities on the hillsides were obliterated. The investigation that followed was a legal and scientific battlefield. It revealed that the models used to predict the landslide were critically flawed. They had tested scale models, but they had used gravel instead of sheets of rock. Gravel behaves like a fluid. It slumps. Sheet rock behaves like a rigid body. It slides. By using the wrong material in their simulation, they predicted a slow, safe decline. Reality gave them a catastrophic shear failure. This distinction between a slump and a slide is the difference between a wet basement and 2,000 deaths. It highlights the absolute necessity of accurate variables in scientific modeling. You cannot approximate geology when the stakes are existential. The Vajont disaster is a reminder that the Earth is not a static stage for human history. It is a dynamic, violent system. We build our civilizations on a crust that is constantly moving, shifting, and adjusting to stress. When we intervene in these systems, when we block rivers and saturate fault lines, we become part of that stress equation. The kinetic energy that destroyed Longeron was stored in Monte Toc for millions of years. It was sunlight trapped in ancient chemical bonds, rock lifted by tectonic plates, waiting for gravity to reclaim it. All it took was a layer of wet clay to pull the trigger, to decode the chaos, and survive with science. Stay connected to Surphysia.